Today we're going to be talking about three of the objectives from our unit, 3.3, 3.5, and 3.6. All of these objectives explore how the quantum model of the atom helps to explain some of the properties that we see with respect to energy and light. So our goal today is that you can be able to describe what happens as electrons move within their energy levels and what evidence we have to support those claims and be able to characterize parts of a wave. Now, a wave has several characteristics that we can define. Wavelength is represented by lambda, so that kind of upside down Y looking thing. That is representing the distance between the peaks, the crests, or the troughs. So as long as it is the same position on the chart, that is going to be your wavelength, the distance between them. Because it is a distance, the unit is measured in meters. Frequency is how often the wave cycles past a given point at the same position on the wave. So typically this is measured in 1 per second or hertz. That significance of that 1 per second is going to become very important as we do calculations and cancel out units. Amplitude would be the wave's height from the 0 point or the origin to the crest. This is significant oftentimes in intensity or how intense the wave is. I know it's the same thing. Now, the electromagnetic spectrum is the representation of all different types of energy that are characterized by frequency and wavelength. We have very high energy waves on the gamma ray side and the X-ray side, and we have very low energy waves on the radio wave side. In the middle, in a very narrow range, we have the visible spectrum. These are the colors of light that you can see. So for any of these different waves, we can characterize them by their wavelength, their frequency, and the amount of energy that they carry. Now here we see a great diagram that helps to represent those relationships between frequency and wavelength and energy. You'll notice when it's high energy, you have the wavelength is very short, and it appears in the diagram that the wave is almost like squished together. Think about that as hitting something really, really quickly. When you think about that, it's like lots and lots of impacts. It would really cause a lot of damage if that were the case. Low energy waves, think of it as like a gentle wave along the ocean. Not going to be as much damage as that hits as opposed to a really intense, quickly moving wave. So when you think about the visible spectrum, notice that right outside of it, we have the ultraviolet region. So just to the higher energy side, remember that's the stuff that can cause damage from the sun. So one of the reasons is because it's a higher energy wave, it has the potential to do more damage to cells and DNA. Infrared is the region just below red, lower energy than red, and we actually can take advantage of that in terms of sensing heat and things like that. Now, when we started to tie this into the atom, quantum theory was really developed out of some observations. Planck noticed that hot objects would emit light. So you're adding energy in the form of heat, and we saw a response in the form of the emission of light. He concluded that energy is emitted in small, specific amounts and called them quanta. A quantum is the smallest amount of energy emitted or absorbed. When you think of this, they used to assume that atoms could absorb and emit any amount of energy. So on the left, in classical theory, we see a man walking up a hill. Assume that that would be, I could stop anywhere on the hill and record the amount of energy that was used to get up that hill. In quantum theory, what they started to represent the model and modify it is it was more like a staircase. If you wanted to go from one stair to the next, there was a defined amount of energy represented by the height of the stair. I can't stop halfway between a stair and the next. I have to either be on the one above or the one below. So when we look at quantum theory, the way we modified our model of the atom is that there were these specific energy areas or amounts of energy that could be taken on, which would be represented by going up and down the stairs. Additional evidence to support this is the photoelectric effect observed by Einstein. What he concluded is that light has properties of both waves and particles. What they observed is that if you applied a wave to an element, At some point, the energy would be high enough to eject an electron. So here in the left, we see that the red or low energy wave did not have enough energy to kick the electron out of its spot, to push it out of its energy level. This is more about what we know now. But if the wave had enough energy, an electron would be pushed out moving at a particular speed. They could determine the wavelength of these energies and therefore the frequency and energy, and then calculate that out and relate that to the energies of the elements. A photon is the name they gave to a particle of light that carries a certain quantum of energy. So a photon, think of it as like a packet, a release, a particle, just like an electron is a particle. And for it, we can identify and measure its wavelength and frequency. Connecting to this, one of the things that we saw with Planck is that iron does emit light when heated. What's happening is that as it gains energy, it will emit different colors of light. And what they identified is that each color has a specific wavelength and frequency that can be determined. If you can identify which wavelength and frequencies are released, we can determine the amount of energy that's gained or lost. Whatever I gain is the same increment that I lose in. And that's connected back to what we call quanta. So when we connect this to actual atoms, there's a couple things that we can connect to. We already know that the electrons exist in energy levels. Those are the possible areas where electrons can exist. We've established through our Pogel activity that ground state is when all of the electrons filled in the lowest energy levels possible using all of our rules of placement and electron configurations. That is a stable conformation. However, when energy is applied, we can push them into an excited state. If electrons take in energy or absorb it, they are able to get moved to higher energy levels further from the nucleus, and that makes it an unstable atom. So here, to summarize, if we add energy to the atom, when the electrons go to higher energy states, what they are doing is moving further from the nucleus. This establishes an excited state. Some of the most common ways to add energy is through heat or electricity. Losing energy occurs when the electrons return to ground state. So if they get pushed out, we said that's an unstable state of being. So the electrons will fall back down to normal. When they do that, they give up those packets of energy, those photons, in the same increments that they absorbed. Again, because we can measure wavelength and frequency of these photons, we can determine the type of energy that's released. One of the things that we do see is the energy of a photon is proportional to its frequency. That means as the energy increases, so does the frequency. We are then going to do something called a flame test. One of the things that we see is that many metals have their emissions in the visible light spectrum. So this certain amount of energy that they absorb and emit is in one that we can visibly see. And those colored lights are very typical for certain types of elements. Now, normally, when we look at white light, like something coming off a light bulb, it would be considered the continuous spectrum. It is a blended band of colors that results when you pass light through a prism. The prism will split up the colors based on their wavelength and frequency. When many electrons are jumping all at once, we see all of these different colors emitted. Now, if I look at a single type of element, because the elements have their electrons in different arrangements and in specific energy levels, we're going to see the electrons drop in certain patterns. Those patterns will produce emission lines, or specific amounts of energy that are produced when those fall. Here we see emission spectra for 5 different elements. And because the patterns of electrons in each are different, we see different productions of emissions. So the red ones represent low energy emissions. Okay, the purple end represents high energy emissions. These represent energy that was released when electrons dropped energy levels. The bigger the drop, the greater the energy. So on this end, you might have dropped from like energy level 6 to energy level 2. Over here, maybe it was a single energy level drop. hydrogen, being an element with a single electron, we can actually tie the specific drops to certain wavelengths. So because hydrogen has a very specific arrangement and much fewer emission lines, we can be more confident in the patterns that we see. What was happening during the flame test lab is that as you heated it and excited those electrons, when they fell back down to normal energy levels, you saw a...
This is a reminder for the members of...
Sorry about that, caught the announcement. The electrons are falling back down, and you're seeing the most dominant color emitted in their emission spectrum. Now, when we take a look at the electromagnetic spectrum, unlike frequency and energy, frequency and wavelength are inversely proportional. That means that as frequency of the wave increases, the wavelength decreases. So if you take a look back at the diagrams that we have, you'll be able to see that pretty clearly. You don't have to do the calculations for regular. And for energy and frequency, we said they are proportionally related. So the higher the energy, the higher the frequency. Now, make sure that you summarize some of the key ideas. What I would recommend, you need to go back to your periodic table, your objectives. Look up objectives 3.3, 3.5, and 3.6, and write one summary statement for each.